Hi there everyone, welcome back to Cody's Lab. So I'm currently on the beach of the Great Salt Lake at Promontory Point, Utah. This here is a peninsula that extends out into the lake, but it's also one of the longest straight shots on a level surface, the surface of the lake, to a major landmark. You see over there is the Kennecott smokestack, about 35 miles away. It is the tallest man-made structure west of the Mississippi River and is almost as tall as the Empire State Building. So given that I know how tall the smokestack is, how high it is above the surface of the lake, and I know how far away it is, about 35 miles, I should be able to, by looking at it, estimate what the curvature of the Earth is. And if the Earth is not round and is actually flat, like some people seem to believe, then we should easily be able to see the Saltaire Building and the highway that runs along the lake. The Saltaire Building, of course, is very recognizable as well. So I've got a camera hooked up to the telescope so you can see through it. So now if I can just see the screen on the laptop, I'll show you guys what's going on. So here we go, the telescope's pointed at the opposite shore, and there's the horizon. Now, if we can just move this along the lake, we should be able to find that smokestack. Okay, it doesn't appear to be that way, so I'm going to turn it back. Looking out over here. Let me adjust this telescope upwards. You can see the mud flats and the lake surface. And there's the smokestack right there. You can see a bit of its reflection. That's interesting. Yeah, look at that. You can see the mountains in the background. There we go, we can see it. But one thing we definitely cannot see is the highway, which should be visible from here. And also the buildings, the smelter buildings, which should be right over there in the middle of the screen. They are not visible either. And Saltaire should be over here. Should be right about there, but is below the horizon and we cannot see it. So there you go. The Earth is round and it is hiding things behind its curvature. Now, based on this image here, I should be able to estimate how much of the tower I can see and roughly calculate how round the Earth is. So now that we've gotten some pictures from the lake level, on the beach, we've now come up into the hill. So we're now about 100 feet above the lake level. I would have liked to have gone up higher, but unfortunately there was a lot of no trespassing signs. So now we should be able to see more because we're up higher and the horizon should be farther away. So let's get this set up and see what we can see from here. Yeah, now that we're in the shadow of the truck, I can actually see the screen. Excellent. Lens cover's on. Let's pull that off. Okay, let's adjust the camera so the horizon's level. Okay, look out off to the edge. So that there is the edge of Fremont Island. Now we turn this to the right. Oh, I can see some tanks. It's part of the structures at Kennecott. We can actually see them from here. And there, of course, is the smokestack, which still, despite the fact we've come up a little bit, I still probably can't see all of it. I still don't see the highway. Let's see. Oh, there's a bird. Let's see if I can see Saltaire. Saltaire should be right around there somewhere. I still don't see Saltaire from here. Alright, well, there you go. But you can see those white tanks now. We couldn't see those before. They've come up out of behind the horizon. And there's the tower. It certainly looks taller, but I'll have to do some pixel measurements back home. So now that I'm home and can review the footage, the first thing I've noticed is that the quality of the video, especially the one taken from the beach, is very poor. This is mostly because I'm looking through an equivalent mass of air of over 150 feet of water. There was more air between me and the smokestack as there was between me and space. So atmospheric effects are going to be rather significant. And if you look at the mountain, you can see many of the rocks and geologic features are actually replicated just below themselves. This is what's known as an inferior mirage, and they're actually quite common. So what you have is the ground surface and a thin layer of air above the ground, which has a lower density than the air above it. So when you have an object over here, like say your mountain, the light can come down directly to the observer. So here's my little telescope. But it can also come down like this, and actually, because light travels faster in a low density medium, bend up and come out a second direction. So yeah, you end up with two images of the same spot. This low density gas layer is of course caused because the sun is heating the water and causing a small amount of warm air to build up close to the ground. This layer is probably no more than a few inches to feet thick. Now if we're working on a curved surface, the surface of the Earth, then we have the layer going around like this. Now what we have is our detector here, and you can have light come in from your source either directly without being changed at all, or it can come down and get deflected upwards a little bit, coming in from a slightly different direction, showing two different images. Now if the light is released from below the horizon, then it will come out and get deflected upwards as well, but in this case it's going to go off into space and it'll never reach the detector. If the light is released exactly level with the horizon, or the top of the gas layer, then it will come to the detector without being deflected at all. Now it is possible to see things that are below the horizon if this air layer has a higher density than the surrounding air. Now that's a rare thing to happen because sunlight tends to warm up things. It doesn't cause things to cool down. So really the only way this could happen is if you have a bunch of cold water down here and a warm air mass comes on top of it, and you end up with some air that's cooled by the water. But anyway, in this case, light being released below the horizon gets bent downwards. So it could either run into the ground sooner or get bent down like this and actually come out a little bit sooner than it would have, or the light can actually get bent in such a way that it follows the curvature of the Earth and then comes out and gets detected by my detector. So in this case you can have things visible below the horizon, but not very much below the horizon. And this is also not what's happening here. So what's this mean? Well, it means that if I've got an image, say you've got the two gullies coming down, and then I've got two reflected gullies coming back like this, it means that the actual horizon is right between the two. So I can use this for the measurements. So here's the video of the smokestack from the beach of Ponmatory. Let's take just a screenshot of this right there. Okay, and now let's take that screenshot and let's load it up into MS Paint. Now if we take the tower and we outline it, so we take this line tool and just sort of go up the side of the tower so we can get what it's what the side actually is, because it's kind of hard to see. So we take this other side, let's mark this as well, average out all those little atmospheric disturbations. Okay, and let's zoom in on the top here. Okay, and let's just measure the distance between these 2 points, which is the top of the tower, which I know in real life is 40 feet wide. So I'm getting, looks like 25 pixels long there. So 40 divided by 25 is 1.6 feet per pixel. Let's go back to the paint. Let's zoom back out, and let's put in the horizon line. So you can see these two replicated gullies here. Let's go right between those, and there's a little spot over there that looks like it's replicated. So right along there is the actual horizon. Everything below that line is a reflection. Okay, so let's measure from the top down to that line, see how much of the tower we can actually see. So that is 434 pixels long. And then multiply that by 1.6. So times 434 gives me 694 feet. So let's call that 700 feet of the tower is visible. So now if we take the surface of the lake, which is right there, which I know to be 4,200 feet of elevation, the smokestack, which is actually up on the hill, is sitting at, let me see, 43, 44 feet. And then the smokestack continues up an additional 1,215 feet. Okay, so if we can see the top 600 and 700 feet, then that means we've got 520 feet of the stack which is hidden, and an additional 144, so that is 644 feet which is hidden from our view. See if we can use that to figure out the radius of the Earth. Okay, so let's draw in the planet, which is, as you know, round. So here we go. Now I'm going to draw two lines, one from the radius of the Earth out to the top of the tower, and one from the radius, or the center of the Earth, to the observing side, just like this. Now we take a line which is tangent to the surface of the sphere at our observing location, so that's going to be right there. Okay, so this number here is going to be the height of the tower, and this is the radius of the Earth, and this is the radius of the Earth. We're assuming we're viewing it from 0 height, and this should be a right angle. So since this is a right angle, we should be able to use the Pythagorean theorem, a squared plus b squared equals c squared. So our a, ground length, which we know because I was able to look at a map and figure out how far away the smokestack was. Now of course this won't be actually this a, because the curved planet is a slightly different length than this long arm here. But of course, since we're talking about a sphere that's so big it's practically flat, the differences will be negligible. Okay, so now all I've got to do is solve this for b or our r. So this is our b. So our c squared number in this equation is going to be, so c equals h plus, so c is going to equal h plus b, which means c squared is going to look something like this. So you've got b squared right there, and then you're going to add a little bit to each side, so like two rectangles here, and a little square off to the corner there. Now the length of these are going to be h, and the width here is b. This here is going to be h squared. So given that, we should have 2hb for the area of these areas here, plus h squared for that. So this is what our c squared equals. A squared equals c squared minus b squared. Now we found c squared equals, so that's a squared equals b squared plus 2hb plus h squared minus b squared. Now b squared cancels, they're positive negative, so a squared equals 2hb plus h squared. Now dividing by 2, dividing by h gives us 1/2 a squared over h minus 1/2 h equals b. That's the radius of Earth. So now all we got to do is plug in the numbers. Now we know that a is the 192,720 feet. So plugging those in with my calculator, I get b equals 279 million. Divide that by 5,280 gives me 5,296.8 miles for the radius of the Earth. I happen to know that this is an overestimate. The actual radius of the Earth is closer to 4,000 miles. But, you know, this is a number, and it is decently close to the 4,000 value, which is given by far more sophisticated measurements than what I have here. So I think that's pretty good considering how simple of a measurement system I had here. But I do have one more measurement from up on the hill where the effect of the atmosphere is not quite as bad. So maybe that will give me better numbers. So to get this other number, I have the video from the 100 feet up, and you can see the white tanks, and we can look at the mountainside here. We can see that these little slide gullies there, the base of them is the base of our view of what we can see. So let's actually load up Google Earth. I had this open earlier. So here's this, here's that, and the horizon is right about there. Right about where that road is, in fact. So let's just go over straight from that, and it looks like 4,500. Yeah, looks like 4,500 feet of elevation. Okay, let's see what that number gets us. With the new numbers, I have a feeling this will be a much more complicated problem, but it should be doable. So it's drawing the radius there, and the radius here. Now, this is not going to be a right triangle, because we're not looking out tangent to the circle. You see, that would be if we're down here on the ground, since we're up here in the sky by about 100 feet. We're looking out over the circle at a line that intersects it just once. Along here, along there, like that. Which means a line drops straight down from that point to the center of the Earth is going to be a right triangle. So this is going to be our S, that has smokestack we can't see, and this is H. So the big problem here is we don't know where this point is. So this is A1, A2, both those have the other A, which equals 36.25 miles in this case. That's not far away from the observing site. So at the moment, the best way I can think of to get that ratio is to, well, make a circle and then do the ratio basically on a smaller scale. All circles should be the same, so it should work out, right? I might be doing it wrong, but I spent an embarrassingly long amount of time trying to figure this out. So let's take this, so 2 units. So that's going to be our 100 height, and then over here I want 2 times 3, so that's 6. So I want 6 units high. It's going to be right there. And I just measure the distance between these. That's like 22, and this one is 12, 13. Okay, it's probably very rough, but also probably fairly decent. So it's 13 divided by 22, that's 0.591, so basically 0.6. Let's plug that in and see how it does. So here's our triangles. Now I should only have to solve for one of these because the b is the number that I'm trying to solve for. So I can use the same equation that we used up here on this first problem. So now A1 is 0.6 of 36.25 because the 36.25 miles is the total A number for this observing location. So that's 36.25 times 0.6. So that means A1 equals 21.75 miles. Okay, so I'm going to square that, divide by 2, divide by 300, so here's our height right there. Subtract 150, which is much, there you go. And so that should be in feet, and if I divide that by 280, you get miles. That's 4,162 miles. So that's a far sight closer to the actual number. So yeah, there you go. It is possible to measure the radius of the Earth to a decent level of precision. I'm sure that most of my error now is actually in this calculation. Like, I don't know how precisely these ratios are 22/13ths. So, and also I'm not sure if that's actually a legitimate way to do this problem, but there you go. And of course, since I posted this video before with the wrong answer, I got the right answer almost immediately. I think Sean went through and used an online algebra solver to do the problem, and he came up with an answer of 4,685 miles, which is off by about 18% of what the Earth's radius is. So I was fairly close, but yeah, so if you do it more correctly, the number is a little bit more off even. But that is, of course, probably because of the mirage effects that I talked about earlier. Anyway, I think I will actually post this video as a new video. I believe that with YouTube's new system, I actually forfeit some or all of the ad revenue from the first video, but you know, I'd rather be right. So there you go. Hope you all enjoyed. I'll see you next time.